Okay, this is AP, AB, and BC Calc. We are doing Unit 3, Section 6, which is calculating higher order derivatives. So far we've been dealing with the first derivative of functions, and we're going to start talking about second derivatives and third derivatives and so on. All right, so here's a note about notation for higher order derivatives. So far we've actually seen three notations for the first derivative. We've seen dy dx, we've seen f prime, it could be g prime or h prime, but you get the idea, I used f here. And so f prime of x, and we've seen y prime. I want to show you how those three notations change as we take additional derivatives, right? So the second derivative, meaning the derivative of the first derivative, if you differentiate the first derivative, you get d squared y dx squared. That's this first notation. The second notation would be f double prime of x, that's how we read it, f double prime of x, or y double prime. The third derivative would be d cubed y dx squared, or dx cubed, my bad, over f triple prime of x, or y triple prime. Now, after 3 primes, and you can sort of see it happening here, that's a lot of little hash marks to read that are tiny little superscripts. So eventually we start using a number here instead. What I want you to notice is that we're using the number that is written in the exponential, like superscript position. It's not an exponent. It's in parentheses, and it means derivative. So d4y over dx the fourth is the same as f 4 primes, or the fourth derivative of x, or y with that 4. So what I want you to notice here is that, like, y to the fourth means y times y times y times y. But y with a 4 up in the superscript in parentheses means the fourth derivative of y. Okay, so we see the difference, right? So y with a fourth as an exponent means y times y times y times y. Y with a 4 up in parentheses in that superscript position means the fourth derivative. So to get the second derivative, we differentiate the first derivative. So we'd have this first derivative, we'd differentiate, get the second one. Then we do it again to get the third, and so on. All right, so we're going to find the second derivative of this function. So I would suggest you're probably more comfortable writing this as a 1/8 in front of the x to the fourth. It's up to you, though. I don't care. All right, so there's my first, there's like my starting function. So the first thing I have to do is find the first derivative. So I'm going to drop that 4 down in front. So 4/8 gives me a 1/2 x to the third. And then when I differentiate this, it's going to be a chain rule, right? The derivative of cosine is negative sine of the stuff, but there's stuff inside the cosine, so I have to multiply by that derivative, which would be 2. So before I differentiate again, I'm going to clean this up and make this a positive 2 sine of 2x, right? So that's my f prime of x. Now I'm going to differentiate again, right, because it said second derivative. So f double prime of x is going to be a 3/2 x squared, right? And then when I differentiate the sine of 2x, this is 2, derivative of sine is cosine of the stuff, right? But since there's stuff inside the cosine, you need to multiply by the derivative of the stuff. So I'm going to get that my second derivative is a 3/2 x squared plus a 4 cosine of 2x. So again, there's not a shortcut here to go from the original function to the second derivative. When you're finding the second derivative, you have to go through the first derivative. And there are sometimes some exceptions to that because of some tricks that we'll see later in this video. All right, so go ahead and give this a try. You can pause me if you want, but you're going to find the second derivative, right? So remember, that means that you have to differentiate to find the first derivative and then differentiate again. So I'm going to get a 15x squared. And then notice that this is a chain rule because there's something inside the e function. It's e to the 4x, not just e to the x. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So I get that my first derivative is a 15x squared plus a 4e to the 4x. Now remember, I told you early on in this class that we mostly simplify selfishly at this point. The reason I bothered to simplify this mess after I did it was because it's going to be easier to differentiate this if I've already simplified. So again, a lot of our simplifying is going to be selfish at this point. So when I differentiate the 15x squared, I get a 30x plus 4, derivative of e to the stuff is e to the stuff, but I need to differentiate the stuff, right? So I get that my second derivative is a 30x plus a 16e to the 4x. All right, we're going to go ahead and find the second derivative of secant of 3x, right? So the derivative of secant is secant tangent, but notice there's a function inside the functions. The derivative of secant of something is secant of that thing, tangent of that thing, but I need to apply the chain rule and differentiate the thing inside. So I'm going to get that my f prime of x is a 3 secant of 3x tangent of 3x. which is great, but now I'm asked to differentiate again, and I suddenly have a situation, because this is a product rule, right? I'm going to clump that 3 coefficient with the first function. It doesn't really matter which one you put this with, but I'm just going to put it with the first one. So when I go to find f prime, double prime of x, I have u, which is 3 secant of 3x, dv, well, that's going to be the derivative of tangent 3x. The derivative of tangent is secant squared of whatever was in the tangent, but I have to use the chain rule and multiply by 3 for differentiating the 3x. So that's my u dv plus my v, which was just tangent of 3x, right? And then du, which I'm going to squeeze down here, du is 3 times the derivative of secant 3x, right? So when that's my u, so when I differentiate, I'm going to get 3. Derivative of secant is secant of the stuff, tangent of the stuff, which in this case is 3x, times the derivative of the inside, which is a 3. So when I clean up my f double prime of x, I'm going to get that this front thing seems to be a 9 secant cubed of 3x, right? Because there was a secant times a secant squared. And then in the back, I seem to also have a 9, right? A 9, there's 1 secant, and there seem to be 2 tangents, so secant and then tangent squared. Now that's great. If you wanted to take out a GCF, you could definitely take out a 9 and also a secant, and that's fine, right? So if you wanted, you could take out a GCF that was a 9, so just to show you what I mean by that, my f double prime could be a 9. I could take out a secant of 3x, and what seems to be left is a secant squared plus a tangent squared, so secant squared of 3x plus a tangent squared of 3x, which is also fine. So that answer's great too, right? In terms of answers like that, again, most of your simplifying and factoring is done selfishly because you're asked to do something with a function. So I would probably leave my answer like this. Could they use some trig identities to try and make you have a different answer that is the same answer as this but looks different based on some trig identities? Yes, it's not likely, but it's possible. It's why it's useful to know your trig identities. All right, so go ahead and try a P2. Again, you're going to find the second derivative of this function. You can pause me if you want. So this is definitely a product, and in that product there is a chain because there's a negative inside the e to the x. So my first derivative, f prime of x, is going to be u. dv is going to be e to the stuff times the derivative of the stuff, right? So that's my u dv, plus v, which will be e to the negative x. du is just going to be a 4. So when I clean this up, I seem to get a negative 4x e to the negative x plus a 4 e to the negative x. So that's my first derivative. When I go to differentiate again, now there are some options here. You will see some people that would choose to factor this. So if I choose to do this, I'm going to notice that there's a product in the first part of this. There's my u and my v, and there's not a product here. That's nice. That's just a coefficient. So when I differentiate and get my f double prime of x, and notice the importance of putting the correct number of primes and clearly indicating that f prime is not the same as f double prime. U dv is going to be a chain, right? Derivative of e to the negative x is e to the negative x times that negative 1, plus v du, right? And then I'm going to differentiate this thing that comes after the product, which is just going to be a 4 e to the negative x times a negative 1 because of the chain, right? With that negative 1 is the derivative of the negative x. So I'm going to get that my f double prime of x is a 4x, because this negative times the negatives, e to the negative x, and then what seems to be a minus 8 e to the negative x, right? Because there's a negative 4 e to the negative x and another negative 4. So you will often see this one with a GCF factored out, which would be a 4 e to the negative x, and what you'll have left is an x minus 2. The reason you'll often see this factored, so this answer is great, but you'll often see it factored because you're very frequently going to be asked to find when this thing is 0 or positive or negative, and factoring is the easiest way to do that. As a side note, some of you might have spotted that at this stage, you could have written f prime differently, and it would have given you a different product. If you had factored f prime of x and pulled out, let's say you pulled out a negative 4e to the negative x, what would have been left would have been x minus 1. You then could have done this as a product, where this is your u and this is your v, and I promise you're going to get the same answer. It just looks a little different. If I did it this way, my f double prime of x would be u, right? I just copy u. dv is a 1 plus v, which would be x minus 1. Du is going to end up being a negative 4e to the negative x times the derivative of that negative x, right? So when you clean this up, you're going to end up with this negative 4e to the negative x, right? That's this thing. And then you're going to end up with a negative 4 or sorry, positive 4 rather, because this is negative times a negative, x e to the negative x, and a negative 4 e to the negative x, which if you clean up is exactly the same answer that we just got. So you'll see that this gets you right to there, and that's fine. So remember that there are often multiple routes to the same answer, and there's nothing wrong with that. All right, let's go ahead and do an E3. So we're going to find d squared y dx squared in terms of x and y. This clue right here, in terms of x and y, that's pretty much code for, hey, you should do this implicitly. Okay, that's code for, hey, you're going to have x's and y's in your answer. So I'm going to go ahead and differentiate. So my first derivative, right, I'm just going to put 1 there, 2x plus the derivative of y squared is 2y dy dx, because I just differentiated some y stuff, and the derivative of 36 is a 0. You will be shocked by the number of times that you will forget this and accidentally write a 36 here and then get mad at yourself. I need to solve for this first derivative before I can do anything else, so I'm going to subtract the 2x over, right? I'm going to get 2y dy dx equals negative 2x. dy dx is going to be negative 2x over 2y, which I'm going to just write as negative x over y. So I need to find the first derivative before I can find the second derivative. So my first derivative is negative x over y, meaning I need a quotient rule. I have a high function, I have a low function when I differentiate again. So now, when I go to differentiate again, right? So now when I go to do the second derivative, I'm going to differentiate with respect to x, this dy dx equals negative x over y. And what happens when I do that is when I differentiate the first derivative, I get the second derivative, d squared y dx squared. And actually, you can kind of see why the notation works the way it does when you look at this, because it's d of dy, so 2 d's and 1 y, d squared y, and then dx quantity squared, right? So d squared y dx squared. On the other side, I'm going to have low d high minus high, and then d low is going to be a dy dx, and that's important because I'm differentiating y stuff, so it's a dy dx. On the bottom, I'm going to have a y squared. What that means is when I clean some stuff up, I need to replace this dy dx with what dy dx is, which is a negative x over y. So I'm going to get that d squared y dx squared is a negative y plus an x times this negative x over y, all over a y squared. Now remember, we simplify selfishly. This answer is not wrong, but there is no way this is the multiple choice answer they're going to give you. So this is a negative y actually over 1, right, minus an x squared over a y, all over a y squared. So let's clean this up a little bit more. If I have fractions in my fractions, I need to get a common denominator. So I'm going to multiply this fraction by y over y, which I'm allowed to do because it's 1, because that'll give me a common denominator of y. So I'm going to get negative y squared minus x squared, all on top of a y, all on top of a y squared, right? Remember that y squared is actually over 1 on the bottom, so this is a negative y squared minus x squared over y times a 1 over y squared. So it's possible you're going to see the answer as negative y squared minus x squared over a y cubed. That's a possible answer. However, if I were the AP Calc exam, it's not the answer I would give you. So it's not wrong to have your answer as d squared y dx squared equals negative y squared minus x squared over y cubed. But the AP is tricky. So if I were the AP, the answer I would give you, so my likely AP answer, if I were an AP multiple choice question, my likely AP multiple choice answer would be a negative 36 over y cubed. And you're probably like, oh, hey Hogan, where on earth did you get this negative 36? Well, let's go back up for a sec and look at this. The original value of the function I was given, if I extend my page a little bit, remember that the original, right, recall that we were originally given that x squared plus y squared is a 36. So now look at this numerator. Isn't this numerator a negative in front of a y squared plus an x squared, which would totally be a negative in front of a 36, which is how this is the answer the AP would choose to give you. Now, again, this answer is totally right, but I just want to throw out there that a huge part of what makes the AP hard is sometimes they throw in a little bit of extra simplification at the end to make sure that your multiple choice answer matches, which is tricky and kind of mean, but it is what it is. All right, so you're going to go ahead and try the same thing. You're going to find d squared y dx squared in terms of x and y. Again, this is a hint that they want you to do it implicitly, right? They're saying, hey, we know you probably could solve for y, but hey, we want the answer in terms of x and y. So go ahead and pause me if you want, and I'm going to walk through it. So my first derivative is going to be 3x squared. The derivative of natural log of y is 1 over y times a dy dx, and the derivative of the 5 is a 0. When I solve for dy dx, I'm going to do that by subtracting the 3x squared over. So I'm going to get 1 over y times this dy dx equals a negative 3x squared. And I'm going to multiply the y over. So I'm going to get that my first derivative, dy dx, is a negative 3x squared times y. So that's my first derivative. What that means is that I now have a product rule, right? So I have a u times a v when I differentiate the second time. So when I differentiate again, my second derivative, meaning the derivative with respect to x of dy dx, is d squared y dx squared. And then I'm going to get a u. dv is just going to be a dy dx, right? Because I'm differentiating y stuff. So this is my u dv. Plus v, which is the y, du would be a negative 6x. So since I'm supposed to give my answer in terms of x and y, the last thing I have to do is I need to replace this dy dx with what dy dx is. So my d squared y dx squared is going to be negative 3x squared times a negative 3x squared y plus a negative 6xy. I'd probably clean this up and get a 9x to the fourth y minus a 6xy. And that's likely my answer. If you want to factor out a GCF of a 3xy, you absolutely can. If you did that, you would get a 3x cubed minus a 2 inside. And that's fine. So again, those are my answers for d squared y dx squared. All right. E4, given the equation for f of x, find the instantaneous rate of change of f prime. Okay, at x equals 2. So here's the thing you have to translate from this. What the AP is asking for, or in this case what I am asking for, the ask here is if you want the rate of change of f, you use f prime. Like the instantaneous rate of change of f is f prime. So the instantaneous rate of change of f prime is f double prime. They're asking for f double prime of 2. So the first step in any one of these problems is to translate. The second step is you need to find f prime of x. Then you need to find f double prime, because remember, you can't get to the double prime without the first derivative. And then you need to plug in 2, right? So the trick is that this one little phrase is actually asking you to translate and do a whole bunch of stuff. So once I know what they're asking me, I then have a course of action of how to proceed. So the first thing you need to do is try and translate what's written in front of you. The instantaneous rate of change of some function, any function, is that function's derivative at the point. So if I want the instantaneous rate of change of f prime, I need the derivative of f prime, which would be f double prime. So let's go ahead and do this. So f prime of x, this nice happy polynomial, is going to be 4x cubed minus 20, or 9, I'm out of 27, come on brain, minus 9x squared plus 10x minus 0, which is gone. Okay, I need f double prime of x, right? So that's going to be a 12x squared minus an 18x plus a 10, right? And then my answer should be f double prime of 2, and I need to convey that information. I need to convey that this is what they're asking me for, and I know it, okay? So I convey that I want f double prime of 2, which is going to be a 12 times a 4 minus an 18 times a 2 plus a 10. So 48 minus 36 plus 10 should be a 12 plus 10, which is a 22. All right. Same thing, instantaneous rate of change of f prime at x equals negative 3. What they're asking for is f double prime of negative 3, and you need to convey that you get that, okay? Even if somewhere along the line you accidentally find the derivative wrong, at least you've conveyed that you comprehend it, and on a free response that's going to matter. So when I differentiate my f prime, I'm going to get negative 6x squared plus 10x minus 4 plus 0, but we don't care. And that means my f double prime is going to be a negative 12x plus 10, which means my f double prime of negative 3 is a 36 plus 10, or a 46. All right, so given the equation of f, find the equation of the tangent line to f prime. Notice that I'm telling you it's not f of x. Okay, so if I want an equation of a tangent line, I need two things. I need a point, right? Remember that this point is going to be x comma f prime of x, because I'm not trying to find the tangent line to f. I'm trying to find the tangent line to f prime. So I need x comma f prime of x. Well, I know half of it. I know that that's a 0. So I need f prime of 0, right? So right away, that says, oh, hey, I'm going to need the derivative, right? The second thing I'm going to need is I'm going to need, so the tangent slope is going to be the derivative of the function, but remember, we're talking about the derivative of f prime here, so my tangent slope is going to be f double prime at that x value. So it seems to me that I need to find f prime and f double prime, and then I need to find those values. So notice that this is a product rule with a chain, right? 2x is the first function that's being multiplied by e to the 3x. The e to the 3x has a chain. So let's find my f prime of x first. U dv is going to be e to the 3x times the derivative of the inside, which would be a 3, plus v, which is e to the 3x. du is just going to be a 2. Now, if all I needed was f prime of 0, I would not simplify this. My logic for that is I can easily plug in and find f prime of 0. So I can find f prime of 0 right now and say that's a 0 times a 1 times a 3 plus a 1 times a 2. Oh, look, it's a 2. Okay, so I now have a point. My point is definitely 0, comma 2. Yay, I've got a point, okay? But in order to find my second derivative, I would really like this a lot better if it were simplified. So I'm going to simplify selfishly, right? So I didn't really need to simplify to find f prime of 0, but it's going to be a lot easier to have a simplified f prime if I'm going to differentiate again. So I have that f prime is a 6x e to the 3x plus a 2 e to the 3x, right? Now, it's up to you. You can either do this as a product with the 6x being your u and the e to the 3x being your v, or you could factor this out if you want. You could take out a 2 e to the 3x, and what you'd be left with is a 3x plus 1, and then you could treat this as your u and this whole thing as your v. You're either doing it as a product rule here and a normal function here, or you're doing it as a big product. It really doesn't matter which one you pick. Remember, you're not going to be asked to simplify f double prime. You just need a number. You need f double prime of 0. So I'm going to go with, I think I'm going to go with this option. I think in this case that's the easier option, but I promise either one works, right? So u dv is going to be a 3 plus v, which is a 3x plus 1. Notice it has to be in parentheses. Du is going to be 2 e to the stuff times the derivative of the stuff. Remember, all I want is f double prime of 0. So this is going to be a 2 times e to the 0 is a 1 times a 3, right? Plus, this is going to be 0 plus 1 times a 2 times a 1 times a 3, right? Cool. So if I do this, I seem to get 6 plus this ends up being 1 times 2 times 3. So I end up getting 6 plus 6, which is 12. So I'm pretty sure that I now have my tangent slope. It's a 12. Once I know that, I can write my answer as y minus the y value equals my slope, which is mx minus the x value, right? That answer's fine. If you prefer, you could also write this as a 12x plus 2 if you solved, right? Now, all of that to say, if you come back here for a minute, right, maybe this is the option you would have picked, and I want to show you that you're still going to get a 12 if that's the option that you picked, okay? So let's say that you said, hey, I really want to do this for my f double prime. So if you did this, your f double prime is going to be u, which is the 6x, right? dv is going to be e to the 3x times the derivative of the 3x, plus v, which was e to the 3x, du, which is a 6, right? And then when I differentiate the back piece, right, it doesn't need a product rule. 2 e to the 3x will just be a 2 e to the 3x times 2, right? So if I wanted f double prime of 0, I'm going to get a bunch of 0 here because of this x, plus a 1 times 6, right? Sorry, that was a 3, and I wrote it as a 2, right? Plus a 2 times 1 times 3. That's definitely a 6 plus 6, which is a 12. So you get the same value either way. Again, it doesn't matter how you do it, but your answer ends up looking like this. Notice that all of this work was required for a problem that is only one sentence, right? Because from this phrase, equation of a tangent line of f prime, you have to translate what you need. And that's one of the things that makes these questions so difficult as we move forward, is that you're going to have to pay attention to little details. Like, we don't want the tangent line of f, we want the tangent line of f prime. You're going to have to pay attention to tangent versus normal line. You're going to have to know to differentiate and when to differentiate once or twice, etc. Okay, so let's keep moving forward. All right, so Same basic problem, I just gave you a different function, okay? So again, line tangent to f prime, not f, right? So your point is going to have to be x comma f prime of x, right? Which we're going to find, right? It's definitely a pi over 3 comma blank, which we'll find. And your slope is going to have to be f double prime at pi over 3, right? Because you want the derivative of f prime, which would be f double prime. Okay, so you can go ahead and do that, but then once you have those two things, you're just writing your answer in point slope, right? So really, the hard part here is that you have to translate what you're asked to do, and then there's going to be some stuff going on like a chain rule. Okay, so my f prime of x, derivative of cosine, right, is negative sine of the stuff times the derivative of the stuff. So I'm going to get that this is a negative 2 sine of 2x, right? Which means that f prime of pi over 3 should be a negative 2 sine of 2 pi over 3. So this does require that you know about 2 pi over 3 on your unit circle. So this point has a y value of root 3 over 2. So I'm going to get negative 2 times a root 3 over 2, which means I'm going to get a negative root 3. So there's my y value. I then need to differentiate again. So f double prime of x, if I come back up here, right? So I'm going to come back up and differentiate f prime. Derivative of sine is cosine. So this is going to be a negative 2 cosine of 2x, right? That negative 2 is just a coefficient, times the derivative of the inside. So I'm going to get negative 4 sine of, sorry, cosine. I literally wrote the word cosine and then, okay, come on, brain. Cosine of 2x. Okay, so my slope, f double prime of pi over 3, is going to be a negative 4 times, well, the cosine of 2 pi over 3 is a negative 1/2, right? It's negative because of the x value. So this is going to be a negative 4 times a negative 1/2, which means I get a 2. So my slope is 2. Once I have these two pieces of information, I just write the answer in point slope, which is actually an algebra skill, right? So y minus the y value equals m x minus the x value. And that's your answer. If you want to add the, subtract the root 3 over because you want to solve for y, that's totally fine. You could, but I would not suggest distributing the 2. There's no reason. Okay, moving forward. All right, so let's talk about a couple special circumstances worth noting. So these are often the source of trick questions on the AP. E to the x is its own derivative, right? So if I told you that f of x was e to the x, I could ask you for the millionth derivative of f of x, and it's still e to the x, because e to the x is its own derivative. Sine and cosine differentiate in a loop, and all polynomials, meaning functions that have positive integer values as the exponents on x, right, or non-negative because it could be an x to 0, they will eventually derive away. And I'm going to spend the next couple of examples explaining you what I mean by that. We're not going to do practice problems on the next few. We're just going to walk through these trick questions. Okay, so E6, e to the x is special. For each function below, find the first 3 derivatives and then use those to write an expression for the nth derivative. So f of x equals e to the x. Well, I already kind of spoiled this in the last slide. The derivative of e to the x is e to the x. The second derivative would therefore also be e to the x. The third derivative would therefore also be e to the x, which means that the nth derivative, which I'm going to write as an f with an n up in parentheses as a superscript, right, would still be e to the x, right? So that's the nice thing about e to the x by itself. Now, e to the 2x is a little bit different because of the chain rule. So when I differentiate e to the 2x, the derivative of e to the stuff is e to the stuff, but I need to times by the derivative of the stuff, so I'm going to get a 2e to the 2x, right? The second derivative already has that 2 out in front, but now I differentiate e to the 2x and get e to the 2x times 2, so sure enough I get a 4e to the 2x. And the third derivative already has that 4 out in front, and when I differentiate e to the 2x, I need to multiply it by 2 again because the chain rule, so I get an 8e to the 2x. So what I want you to notice is it's not an accident if you look at these things, these are powers of 2, and how many primes I have, right? It is not an accident that this is 2 to the first. It's not an accident that this is 2 to the second. It's not an accident that this is 2 to the third. So my formula for my nth derivative, g with that n up in parentheses as a superscript, right, would be 2 to the n e to the 2x, right? Because when I did the first derivative, I had 2 to the first. When it was the second derivative, it was 2 to the second. When it was the third derivative, it was a 2 to the third, etc. Okay? All of that is setting you up to do this one where I give you another letter. So k is some constant, right? So if I were going to differentiate and get h prime, I would get e to the stuff times the derivative of the stuff, right? which means I'm going to get a k e to the kx. If I were to differentiate again, right, there's a k already in front. I have derivative e to the stuff is e to the stuff times the derivative of the stuff, so I'm pretty sure I get a k squared e to the kx, right? If I differentiate again, there's already a k squared in front. When I differentiate e to the kx, I get e to the kx times k, and oh look, it's a k cubed e to the kx. Well, that means that the nth derivative, right, so the nth derivative of h would be k to the n e to the kx. Okay, so that's, again, those are special patterns because e to the x is kind of special, right? So e to the x is often the source of some trick questions. Let's go ahead and move on to the next one. Okay, so sine and cosine are looping functions. So for each function below, we're going to find the first 6 derivatives. Part A is going to help you figure out what I mean by the loop, and then we're going to talk about how often the loop restarts, and then we're going to help predict other derivatives. Okay, so let's go ahead and find the derivative of sine. The derivative of sine is cosine, right? The derivative of cosine is negative sine. The derivative of negative sine would be a negative cosine, right, because it's a negative in front of the derivative of sine, right? And then the derivative of negative cosine, right, would be a negative of a negative sine, which is a sine. Oh, look, we looped, right? So we looped. So then the derivative of sine, so the next derivative, the derivative of sine would be a cosine, but we already knew that because we already differentiated sine once before. And then the derivative of cosine would be a negative sine, and you can see that it's a loop, right? So we've looped back to the beginning again. So what happens is we're going to learn eventually that when you go down this list, you're differentiating, and when you up this list, you're integrating, right? And you don't know how to integrate yet, but it's the opposite of differentiation. In fact, it's often called anti-differentiation. So for me personally, I think it's worth putting a loop. Like if you're in the middle of a calc test. Now, I normally would never say, hey, you should use sines and cosines as just s's and c's. But I've seen a lot of people put this at the top of their paper when they take a test. Derivative of sine is cosine, the derivative of cosine is negative sine, the negative sine is cosine, negative cosine, and then it loops up to sine again. So this is down for differentiate, right? So what's happening is this loops every 4th derivative, right? So what I mean by that is if I asked you for the 12th derivative of sine, I'm going to get sine again. If I asked you for the 40th derivative of sine, I'm going to get sine again. Every multiple of 4, right? So that's what this looks like. I was asked to find the first 6 and then predict the 11th derivative, okay? So let's do that logically. If I'm asked to predict the 11th derivative, I realize that every 4th derivative, right? Every 4th derivative is going to come back to where I started, which was sine. So the 11th derivative should be right before the 4th derivative, or the 12th derivative, right? So the 11th derivative, so f with an 11 of x, should be a negative cosine because it's right before, right? It's immediately before the 12th derivative. And I know that the 12th derivative, as a multiple of 4, will loop back to sine. So what happens right before I loop back to sine? Oh, a negative cosine. So that's the logic, okay? So I'm going to erase and give myself a little bit of space to do these because I know I'm a little bit low on space. So I'm going to put that loop up just so that you're aware of it, okay? So the loop, right? So the loop that we had was sine, cosine, negative sine, negative cosine, right? And so this down for derivative, right? And it loops back to whatever the starting function was. So here it was sine, it doesn't have to be sine. Loops back to the start function at every 4th derivative, right? So the 4th derivative, the 8th derivative, the 12th derivative, it's going to loop back to the start function. So once you realize that, it's actually not impossible to predict what the 18th derivative is going to be. Now, keep in mind that when I throw in a chain rule, it makes life a little bit harder. So let's find the first couple derivatives for g of x and see what happens. So g prime of x, derivative of cosine, right? We know the derivative of cosine should be a negative sine. So this is going to be a negative sine of 2x, but I'm going to have to times by the derivative of the inside, which is a 2. So there's going to end up being a 2 in front. So it is a negative sine. Derive cosine, you get a negative sine. But there's this negative 2 in front because of the chain rule. The derivative of sine, right? So the derivative of a negative sine, and this is a negative sine. So if it helps you to see it this way, you could put the negative with the sine and leave the 2 in front. The derivative of negative sine is going to give me a negative cosine, but again, I have to derive by the inside, right? So what's going to happen is I'm going to get a negative 2 cosine of 2x times the derivative of the inside, which is going to give me a negative 4 cosine of 2x, right? And then when I differentiate again, so what I want you to notice is it's still following this pattern. See how I had a negative sign and then a negative cosine? I know that the next thing that's going to loop in the pattern is going to be a positive sign, right? Positive sign, and then positive cosine, and then negative sine, and then negative cosine, and then, right, and then positive sine, and then we keep looping, right? The only difference is that every time I differentiate because of the chain rule, I'm multiplying by 2. So I'm going to end up getting that this is an 8 sine of 2x, right? And then the fourth derivative, and I'm expecting the fourth derivative to loop back around to the original, which is a positive cosine, and sure enough it does. The fourth derivative is going to be a 16 cosine of 2x, but what I want you to notice is it does loop the same way, but it has a 2 to the fourth. Why is it a 2 to the fourth? Well, because the inside derivative is a 2, right? So every time I differentiate, I'm multiplying by 2, and I differentiated 4 times, so I must have multiplied by 2 4 times, which is 2 to the fourth. So I did ask you to find all 6, so we'll go ahead and find a couple more. So I'm going to end up with a 2 to the fifth, which is a 32, but remember, it's going to be a negative sign, so negative 32 sine of 2x, right? And then my sixth derivative is going to be a negative 64 cosine of 2x. Now, I was asked to predict the 18th derivative. The easiest way to predict the 18th derivative is to recognize that the 16th derivative, right? 16th derivative is going to loop back to cosine of 2x because it's a multiple of 4. So I'm going to have a 2 to the 16th, which I'm totally leaving as a 2 to the 16th because I'm not going to write that number out, cosine of 2x, which means the 17th derivative, right, is going to, so I'm looping, right? So I looped back to the start, which was here. So if this is the 16th derivative, 17th derivative, 18th derivative should be a negative cosine. Does that make sense? So so I can actually jump down to the 18th derivative and say, okay, cool. So the 18th derivative should be a negative cosine, but I know because of the chain rule that there's going to be a 2 to the 18th and then negative cosine of 2x. Right? So that's what my 18th derivative is going to be. The other way to predict it would have been to go look at the 20th derivative and then work your way backwards on the list, right? Instead of going forwards on the loop, you could go backwards. Again, don't stress if this seems hard. These are trick questions. The only reason you're ever going to be asked to find the 18th derivative or the 25th derivative or even the 10th derivative is if it's a trick question. So if you see that, you could be asked to find second and third derivatives, no big deal. But if you're asked to find a derivative that's this high power, it's a trick question, so calm down and figure it out, right? Okay, so last one, we're going to find the first 6 derivatives of negative sine of 3x, and then we're going to predict the 25th derivative. So h prime of x, right? So again, derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative sine is cosine, right? So I'm starting at negative sine. So when I differentiate, it's going to end up being a negative cosine, but because of the 3x on the inside, it's going to end up having a 3 in front. So I'm going to get negative 3 cosine of 3x. And again, if you actually want to see what you're doing, what you're really doing is there's a negative coefficient in front of the sine. When you differentiate a sine, you get a regular cosine. So there's a negative sitting in front of that regular cosine, hence the reason it nets negative. My h double prime of x, right? Notice that I'm multiplying by 3 every time because of the chain rule. So when I derive negative cosine, I should loop back to sine, but I'm multiplying by 3 because of the chain rule. So I'm going to get a 9 sine of 3x, right? And again, the reason for that is what happened was there was a negative 3 in front of the derivative of cosine, and then I times by the chain, which is why I got a 3. But again, there you can kind of notice that there's some faster options if you see the pattern. Derivative of sine is a positive cosine, so here we have this 27, and the reason it's a 27 is because I know with the chain rule I'm multiplying by 3 every time I differentiate. The fourth derivative is going to be, so when I derive cosine I get negative sine, so that's my negative 81 sine of 3x, right? And so the fifth derivative, and then once you start to see these patterns, right, so there my fifth derivative is going to be a negative, and now this was a 3 to the fourth, so this is going to be a 3 to the fifth, and you can write 243 if you want. But I'm going to argue that at some point it's not worth it anymore. So I differentiate negative sine, I get negative cosine, right? Oh, and do notice that at the fourth derivative, I looped back to the original. I started with a negative sign, and look how I looped back to a negative sign. The reason there's an 81 is because of the chain rule. So the sixth derivative is going to be, when you derive negative cosine, you get positive sine. So I'm going to get a 3 to the sixth and then a sine of 3x. So the question is, how do I predict the 25th? Well, I know that the 24th derivative is a power of 4, right? 24 is a multiple of 4, rather. Sorry, not power of 4. So the 24th derivative is a multiple of 4, which means the 24th derivative has to loop back to a negative sign. So it's a negative 3 to the 24th, which, by the way, you really don't want to do, sine of 3x. that means that the 25th derivative is just what happens if I differentiate again. So what comes after negative sign? Well, that's a negative cosine. So I'm going to get negative 3 to the 25th cosine of 3x. And again, these are absolutely trick questions. No one's going to ask you to do this in most cases. If you see it, it's a trick question. If you really hate this and these last couple examples are making you miserable, then you can always skip this problem on an AP. All right, last one. Each function below is a polynomial. What we're going to do is we're going to differentiate 4 times, and then we're going to start to make a conclusion about how many times we would have to differentiate a polynomial till it has till essentially it ends up with a 0 derivative. So for a, f prime is going to be a 3x squared, f double prime is going to be a 6x, f triple prime is going to be a 6, and notice that when I differentiate the 4th time, I get a 0. So what I want you to notice was that the degree was 3, and there were 3 non-zero derivatives, right? After that, so there were 3 non-zero derivatives. After that, if I differentiate again and again and again, they're always going to be 0, right? Because if I'm differentiating the number 0, I still get 0. Okay, so now I have a degree of 2, and hopefully we can make a hypothesis based on that about when this thing's going to differentiate away. So when I derive the first time, I get a negative 10x plus 3, and if I derive again, I get a negative 10, and if I derive a third time, I get a 0, and all subsequent derivatives are going to be 0 then. Right? So they're all going to be 0. So these guys are going to all be 0. So the answer was that here I had a degree of 2, and I had 2 non-zero derivatives, right? And after that, they all become 0. Okay, and then on the last one, we have a 2x to the 5th, right? And I think hopefully we're able to make a hypothesis based on this now. But h of x equals, h prime of x equals 10x to the 4th, and h double prime of x equals 40x to the 3rd, and h triple prime of x equals a buck 20x squared, and the 4th derivative of h is 240x, right? And I only asked you to do 4, but we know logically, right? So that's all I asked for, but based on what we've seen, since this thing has a degree of 5, there will be 5 non-zero derivatives. Right, and after that, after the 5th derivative, they're all going to be 0. So, and you can see that if I keep going, right? The 5th derivative would just be the number 240, which means that the 6th derivative would be the first one that's 0, and then after that, they're all going to be 0. All right, so that is higher order derivatives, and this is the end of Unit 3.